Okay, so today I'm going to take you through how to work a physics problem, specifically this one, and it says two cars are traveling along a straight line in the same direction, the lead car at 24.7 meters per second and the other car at 30.6 meters per second. At the moment the cars are 38.4 meters apart, the lead driver applies the brakes, causing her car to have an acceleration of negative 2.05 meters per second squared. In part A, there's 4 parts. Part A asks, how long does it take for the lead car to stop? So what I have done, and I've pre-done it below, we're going to ignore these other questions for now, is I've written out a key, which does help. As you can see, I've put C1, that's the lead car in green, and C2 is going to be the following car in pink. But it always helps to kind of visually draw out what's happening. So here we have 2 cars in a straight line. C1 is in front, C2 is behind, and they're 38.4 meters apart. With that, I've also gone ahead and drawn this nifty little chart. There's 2 points within this problem that really stand out to me. It is when the brakes are applied to each car and when the cars are stopped. So what I've done is I've gone ahead and filled in what I do know just from looking at this problem up here. And so you can see that for car 1, I'm assuming for all of these the starting time is 0. The position is going to be 0, and I'm just concerned with C1 right now. The velocity is given to us and it's 24.7 meters per second, and the car has a negative acceleration of 2.05 meters per second. So looking at question 1, or part A as I've called it up here, what we need to do, if you can see, or as you can see, there are a bunch of constant acceleration kinematic equations, and what we're going to do is we're going to use these to try to find our unknowns, which is in the stopped section. So part 1 asks, how long does it take for the lead car to stop? And I've rewritten, I also do this with all my questions, I rewrite them not necessarily in easier terms, but just to remind me as I work through problems. So I need to find C1 time when stopped. So looking at these equations up above, and at the same time what we're given, I know I have acceleration, initial position, initial time, initial velocity. I also know that I have a final velocity, and the acceleration is going to stay the same. So looking at those problems up above here, what I want to do is find one of these equations that has parts that match what I have and will give me what I want. So what I'm looking for is time. Now, what I'm going to choose is this problem right here, because I know my final velocity, I know my initial, and I have an acceleration. So what we're going to do is VF equals, that's velocity final, equals initial velocity plus acceleration, and then I'll even draw parentheses there for clarification, times time. Well, my final velocity, actually, scratch that. So what we need to do is we want to solve for time. So what we need to do is rearrange this problem where it equals time. So what I'm going to do is final velocity minus initial velocity, and then I'm left with acceleration times time. Well, I still need to get time by itself, so I'm also going to divide this whole part right here by acceleration. So I have final velocity minus initial velocity over acceleration equals time. Now all we need to do is plug in our points and solve. So we have final velocity is 0 minus initial velocity, which is our 24.7 meters per second. Always add your units, over negative 2.05 meters per second squared acceleration equals time, which equals, when you calculate this out, you'll see that all you're left with, these meters cancel and 2 of these seconds cancel. You're left with 1 second unit, and it equals out to 12.05 seconds. Part A is done. What you can do now that we have this time, it's our final time, so you can go ahead and write it in right here, 12.05 seconds. Now, part B asks, what is the distance traveled? Part B says, what is the distance it travels during this time? Referring to C1, or the leading car. Move back over here. So, as I've clarified again, find C1 distance when traveled when stopped. So we have everything now but our second distance. So looking at this right here in our equations up above, I see 2 problems that will give us distance. We have this problem right here, which has a delta x in it, and we have this problem right here, which is multiple parts and things that can equal delta x. I'm going to use this long one down here because it just flat out gives me x. I don't have to rearrange like I would with this one. So we have delta x, or I'm just going to call it x here. I'm gonna draw my little arrow to say, so I have x equals, so as you can see up here, x can equal either your final distance minus your initial, it can equal the average velocity times time, or it can equal 1/2 times initial velocity plus final times time. Well, I have all these parts right here, so I'm going to go ahead and use those. So I have x equals 1/2 times initial velocity plus final velocity times time. Go ahead and plug all your stuff in. So I have x equals 1/2 times my initial velocity is 24.7 meters per second. My final velocity is 0 meters per second. And now I have my new time up here, which is 12.05 seconds. Totaling all this up on your calculator, you get x equals 148.8 meters. All these units will cancel out. Seconds times the seconds, you're left with meters. Okay, so we have our new x. Let's go ahead and plug it in right here, 148.8 meters. And looking back at our problems as well, we have all units for C1 covered. Now, as the next question will say, we need to move on to C2. Question, part C says, assuming that the chasing car brakes at the same time as the lead car, what must be the chasing car's minimum negative acceleration so as not to hit the lead car? So what we want to find is this acceleration right here, which will also be the same over here, but we need to find the minimum acceleration so it doesn't hit the lead car. Looking back at our equations and what we're given, so we have initial time, we have initial position. We went ahead and said that this was 0 because we're thinking of these cars separately. We have our initial velocity and we have our final velocity. Because the car is stopped, it will be 0. Okay, now looking at these equations up here, we can see that this requires initial and final velocity, which we have, but we don't have acceleration or time, so we can't use it. This problem requires either both distances, which we don't have, or initial and final velocity, which we do, but it also has time. We don't have our time. Now this does not have time, but it still has our distances. What we can do then to figure out our distance, well, we know, looking back at this paper, C1 and C2 are 38.4 meters apart. We also know that C1 stopped 148.8 meters from its initial 0 position. So what we can do is to find our final position where it just doesn't hit it, car 1, is we can take our 38.4 meters and add it to the 148.8 meters of C1 stopping point, which will give us the very minimum of distance of 187.2 meters. That 187.2 meters will be the total distance this C2 car will travel to not hit C1. So now we need to find acceleration. Well, we do have our second distance, but we still don't have time. So let's use this equation right here. So we have final velocity squared equals initial velocity squared plus 2 times acceleration times delta x. Now we need to rearrange this to get acceleration by itself. So we have velocity final squared minus initial velocity squared. And let's just go ahead, instead of writing it out like I did up there, let's just go ahead and divide all of this by 2 times delta x equals acceleration. Well, we know delta x is just final position minus initial position. When we do that, our initial is 0. So this right here, this 187, is actually our delta x. So now we just need to plug in the rest of our values. We have final velocity of 0 squared minus an initial velocity of 30.6 meters per second squared over 2 times 187.2 meters equals, and when you do all the math on your calculator and work it out, you get negative 2.50 meters per second squared. This is our acceleration. And we can put it right in here for both parts now. Oop. Okay. Also should go ahead and put in our x values here because we do have that now. Okay, so now looking back up here, part D says, how long does it take the chasing car to stop? I have a completely new sheet of paper for it. Once again, rewrote it with my colors and easier terms, just to remind me, find C2 time to stop, which coincidentally is the only thing we have left to find over here. So to find C2, and looking back at our equations right here, I am going to use this right here. We already know our final velocity, we know our initial velocity, and we know acceleration now. This is just one simple formula where you can rearrange it really easy and find time. So let's rearrange it. So we have final velocity equals initial velocity plus acceleration times time. Rearranged, we have final velocity minus initial velocity divided by acceleration equals time. So let's plug our C2 values in. Remember what they are. So here we have our C2 values. Final velocity, so we have 0 minus initial all divided by our acceleration, which is our negative 2.5 meters per second squared. Total that out on the calculator and you get 12.24 seconds. This is our time. You write it up here. And now we've solved parts A, B, C, and D, and we have completely filled out our little chart here. I hope this helped.